Hello, my name is Stephen Smith, CAD/CAM consultant here at MyHTT. I'd like to take a minute today and talk about NPRO, a software created by Manufacturing Automation Labs. NPRO allows us to model and understand machining processes at a physics level. So I think the best way to get into this is with a simple example, and this way I can also demonstrate the workflow. So with that, let's just go ahead and take a look at a sample that comes right out of the box from NX. So what I'm using right now is Sim08. It's the cavity mill operation as shown on the left. What I've done is I have left everything the same with the exception of the speeds and feeds, and we'll look into those a little bit later once we get through part of the process. For right now, what I'd like to do is just jump into NX, take a look and see what additional capabilities that we get because of the NPRO plugin. So let me jump out of this. I'm going to jump right into NX. So this is the standard interface that we're all used to working in. As I mentioned, this is Sim08. So one thing I do want to show here is for the operation that we're talking about, the cavity mill. What I have done ahead of time, the only change I've made is I have changed the surface speed to 100 meters per minute, and I've changed the feed per tooth to 0.056. These are out of the box parameters for 4340 steel, and that is just my generic assumption of what this workpiece is. You would, of course, tailor it to your particular application. So to use NPRO, one of the things that's really nice about it is that it's fully integrated within the user interface that we're familiar with. So just up here, I'm going to go to the NPRO tab. We're going to go over to the analysis options. I'm going to select first the material that I'm interested in analyzing. So in this case, like we said, 4340. I have a generic machine that I've loaded in. The machine at the end of the day is a torque and power curve for the spindle. Just helps to ensure that we don't optimize and run out of power on the machine. So if I double click on the operation I'm interested in, which is this cavity mill, what I'm going to do is I'm just going to analyze an existing operation. So this is pretty similar to what you're probably already doing. So you've got parameters that you think are already going to work. You're pretty confident that you're reasonably close to an optimized solution. So we'll go ahead and we'll start off and we'll use that as a kickoff point. You could also use a program that you're already running in production. So I have turned on the things that I'm interested in analyzing, and I'm going to go ahead and hit run here. While this computes, this is going to be a real-time demo, so it'll take a minute or so. What I'm going to do is hop back over to my PowerPoint, and we're just going to discuss speeds and feeds here momentarily. So the tool for this operation is a 12 millimeter ball nose. We're using 100 meters per minute as our cutting velocity, which is pretty midpoint considering that the range is 75 to 120 meters per minute. We are using a feed rate of 0.056 millimeters per flute. The range that is recommended is 0.41 to 0.71. So in this case, I'm just using a GAR VRX series end mill. You, of course, can use whatever tooling you choose to use, and then just go ahead and use the speeds and feeds table provided by the cutting tool manufacturer. What we will be doing later on when we get into our optimization is we will optimize for feed, but we're not going to push beyond a feed of 0.071. And that's because that is the upper range of the recommended operating conditions for this particular tool. I don't really want to push things too far. And I think that even keeping things fairly conservative, we're going to find some pretty impressive efficiency gains. So with that, it appears that the simulation is already complete. So let's take a look at the charts that have been generated for us. So as we kind of mentioned and we thought earlier, power here is really not much of a concern. So it's about 0.7 kilowatts. That to me makes sense. We're talking about a 12 mil cutter that's working on a ball nose, so just the tip of a ball. That, like I said, we're not really concerned with running out of either power or torque in this case. Now, if we take a look at our feed forces, I am interested in trying to contain these a little bit, especially on a finishing or semi-finish. If we can keep our feed forces more consistent, you keep tool deflection consistent, and what you'll end up with is a slightly more uniform surface. So what we see here is the range. So we peak out at approximately 950 newtons feed force, and the recommended range from NPRO's between 758 and 638 newtons. You can, of course, input whatever value you want. In this case, we're just going to use 700. So we want a process that's kind of middle of the line, Of course, by reducing that and not going with the more aggressive, we are going to give up a little bit of optimization in terms of reduction in cycle time, but I think that we can still have a net pretty positive effect, keeping these very conservative values. So I'm just going to exit this. I'm going to go ahead and hit apply here. Once again, I'm going to double click on the operation. I'm going to now go over to my feed optimization tool. We're going to set our maximum chip thickness to 0.071 millimeters. Remember, that is what was recommended by GAR, which is the cutting tool manufacturer in this case. And we're going to aim for about 700 newtons of tool bending force. I'm going to go ahead and make this active. And with that, I will go ahead and hit run. So what NPRO is doing is it's breaking the toolpath up into many little segments. It then analyzes the material to be removed in each segment and uses that data to compute the torque and force values. Now, what's interesting about this is that it's going to end up creating an additional operation in the operation navigation tree that we can post as you would post any other operation. So this doesn't require a new post processor. It doesn't really require anything special either before or after. It's just an intermediary step that we add in. So if you were interested in simulating machine movement through some type of simulation kit, then that would still continue to work exactly as you currently do. It's just that it's going to analyze this new G code. The new G code tends to be approximately 30% longer. So if we take a look at this, so this is still the original graph. What I'm going to do is just close this here for a moment. I'm going to hit apply. And what I'd like to do is just go ahead and redo the simulation with the new optimized parameters. And that's going to allow us to do a quick A/B comparison. While it's doing that, what we see is that even using these very conservative numbers, we're seeing a reduction in cycle time of approximately 11.8%. So this to me is pretty good. I mean, we don't expect to see any significant increase in tool wear because again, we're not applying more pressure to the tool. We're not pushing the tool beyond its recommended chip thickness. So everything is going to stay pretty stable. This is effectively as close as you're going to be able to get to free productivity. It just costs us a couple minutes here to compute and generate these tool paths. So if we now look at the tool force, again, we were aiming for approximately 700 newtons. I'm just going to go ahead and expand the graph. So the original orange process here is what we had just right out of NX as you typically might be running. And the purple is the new optimized toolpath. You'll notice that they don't line up on the x-axis, and that's because the x-axis is set the time. We'll just move these over to a moving distance, just help sync things up and give us a little bit of a better understanding. Now, see, we've got some options here. Personally, I would just go ahead and run this. You're looking at a 12% increase in productivity, no real downside in terms of tool life. If you wanted to push things a little bit harder, what we see is that we're actually down below the orange process just about everywhere compared to where we were, what you were previously running successfully. So you could definitely take that original 700 newtons and push it just a little bit further if you wanted to gain even more productivity. So with that, I'm just going to hit apply. We're going to go ahead and leave this. And now what I'd like to just quickly show you is that now we've got this operation. In this case, it was created as a mill control. It can also just replace the original operation. If I go in and I post this, what we'll end up seeing is that if we post-process this, what we'll end up seeing is that the code is very close to what you would expect. The only thing that's different, like I previously mentioned, we are looking at a little bit more in terms of G code. So what NPRO has done is split up moves. You still get arc moves. All of that still stays the same. It's just that moves now get split up, and each segment of it gets output with a new unique feed rate. So if I scroll to some random point in the code here and we just zoom in a little bit, what we'll notice is that we get new feed rates on pretty close to every line that gets output. So that's just something for us to keep in mind. In this case, I've also got it turned so that we see when the optimization was running and when it was stopped. You could, of course, get rid of just this listing if you don't want to see this in the code. So I hope that this was helpful. I hope this gives you an idea of the capabilities that are available within the NPRO product. If it's something that you would like to see more of or you'd like to have an in depth conversation, please don't hesitate to reach out to us at my HTT. Thank you.